So I'm putting problem 88 next in the list, in the playlist, because I wanted to do a simple pendulum problem, which in the actual in the section on pendulums, 15-6 problems 40 through looks like problems 40 through 56. Um, all of the There's only a couple simple pendulum ones. The rest were just physical pendulums. So I found one in the additional problems, 88, and so I just wanted to do that real quick, just so you can get some experience with the old simple pendulum angular frequency expression, square root of g over L. And in doing problem 88, it brings up a nice little dilemma. Nice little complication, actually, is probably a better way to say it, because you're driving in a car around a circular track while a pendulum in your car is swinging back and forth. So you can imagine that's going to do some interesting things. First off, the length of the pendulum string, which is this little variable here, L, is 20 centimeters, not 26, which we're going to immediately convert to 0.2 meters. The mass of the little pendulum bob is 5 grams, which we're going to immediately convert to. Um, don't even use it, do we? Don't even use it really, so it doesn't matter. But let's just, for the fun of it, because I love converting. It's like my second favorite thing in the world to do. And the velocity of the car, the race car, around the circular track is 70 meters per second, and the radius of this track is 50 meters. Whoa! 50 meters? Holy cow. That's gonna, you're gonna need some friction to hold that car on there. My gosh. Anyway, so let's draw the circular track. This is the top view. We're a little birdie, flying up in the sky, looking down on the car, moving, zooming around the track here. And so, as you know, actually, let's no, that's fine. As you know, in order to move in a circle, you need a centripetal force. In this case, it's going to be friction pulling you in. So let's keep that in mind. Now let's abandon the little birdie. Let's become the person sitting in the car, the driver, looking at our pendulum. So if the car's not moving and nothing is oscillate, if the pendulum is just at rest, at equilibrium, it's going to be hanging down here, right? But if you start oscillating the pendulum, it's going to oscillate back and forth like this, right? Now, typically, all we have as a restoring force is gravity. This is the force that's causing us to oscillate back and forth, right? Unlike the earlier spring problems where the spring was the force, the restoring force. Sometimes gravity, if it, like we were on an incline. Here it's just gravity. But if we're driving, then it's not actually just gravity. So now picture it. We're sitting in the car. The center, let's say, uh, let's say this is the windshield, right? You're looking at the windshield and then the pendulum is hanging from the mirror. So here's the mirror on the windshield, and then you're the driver. This is the driver's side. This is the passenger side, right? And then, of course, if you look out to your right, here's the driver's side window. You got the little mirror. sticking out here, and we're driving. Should I draw the hood of the car? Here's the hood of the car, and then here's the passenger. Alright, I'm having too much fun here. So we're sitting here, and then the racetrack. So we're driving on the racetrack. Here's the racetrack, and then these are the lines in the road. So it's going around this way, right? I hope this is a good enough drawing. And so the center of the racetrack is over here somewhere. So we could look out the passenger window and see the center. So basically, long story short, the circle, the radius of the circle is that way. So we get a centripetal force acting on the pendulum also, which is affecting its oscillations. We're going to need that, because if we redraw this, so here's the pendulum thing. We got the tension force pulling that way, which we're going to ignore conveniently because that's not really going into restoring. We got Fg here, we got Fc here, so Fnet is the hypotenuse between these two. I could just redraw Fg over here, right? And we're actually looking for accelerations because this is really the angular frequency of a pendulum is based off of the restoring acceleration, which normally is just gravity, 9.8. But now, let me actually this is g, and this is centripetal, so this is net acceleration. So A net is Pythagorean theorem. It's the A centripetal squared plus g squared, which is the square root of v squared over r squared plus g squared, right? Centripetal acceleration is v squared over r. And so we're going to actually use A net in here instead of g. So that goes in there. So what this means is omega is the square root of v squared over r all squared plus g squared all over L. And we know all these things. We know V is 70, we know R is 50, we know G is 9.8, L is 0.2. I'm not going to bother plugging those in. I'm just going to tell you the answer, 22.191 radians per second. Thing is, they're looking for, let's see, this is 88. They're looking for frequency, not angular frequency. So frequency is angular frequency over 2 pi. So this is just 22.191 over 2 pi, which is 3.532 hertz. Well, geez Louise. A little tricky here dealing with all this. Hopefully my drawing was sort of clear here. Anyway, if you have any questions on this, let me know. I'll walk you through it further. Bye-bye.